So this is a pretty massive document because all your lessons and worksheets are housed within the same thing. So I'll be skipping a whole bunch of pages because those are kind of your homework questions. But all the homework question answers are in this document, and I believe this document is the second one in the lesson. So the first one will be kind of the same thing but without any answers involved. And then I have this one that hopefully I can just walk you through a little bit just in case it doesn't 100% make sense when you're reading it on your own. So this lesson is going to be a ton of naming different compounds and molecules. So we'll definitely need a periodic table because you'll see a lot of chemical symbols. Some of them maybe you're not so familiar with because they don't pop up too often. So we'd need to kind of consult our periodic table, know what that symbol is for the chemical's name, and also to find out what charge you have for a lot of the elements, because we'll be doing something called crisscrossing, and we'll know what that means by the end of this page, to know how many atoms you'll have of any element in a compound or a molecule. So definitely need a lot of information from a periodic table for both those things. So we're going to have 4 different types of names, and they all kind of have their own naming process that are based on the same types of rules. We'll go through ionic compounds first, and then molecular compounds, which are usually called like covalent molecules. We'll touch on what happens when we have polyatomic ions. These are still just a subset of ionic compounds, the first stuff we had. And then we'll look a little bit at acids. So ionic compounds, what they pretty much are, is when a metal and a non-metal combine to form something neutral. So the way that happens is that the metal is going to give some electrons to the non-metal, and this will lead to an attractive force between the 2 or more atoms involved in this bond. So that's a very brief explanation of what ionic compounds are. Let's figure out how to actually name them. So the rules for doing that. So no matter what, we're always going to have the metal ion named first. So copper, lead, aluminum, sodium, they're all in that massive left part of a periodic table. Periodic table is mostly made of metals, so those metals go first, and then the second part is going to be your non-metal. So chlorine, oxygen, more chlorine, fluorine, these are the elements that are on the right side of the periodic table, and it's a very much so a smaller portion of the periodic table that we'll be looking at. So obviously this doesn't just say chlorine or oxygen. Part of this rule for naming the second half, the non-metal half, is that we need to change the suffix to "ide." So we can always recognize the end of it as an "ide." "Ide, ide, ide." Usually it's very obvious how to change that. Chlorine, the N just changed to a D, but oxygen, obviously we have to toy with it a little bit to make it an oxide. So those are the 2 main rules to naming. Sometimes rule number 3 will pop up with metals. So how I said you need a periodic table just to see the charge of a lot of these elements, you'll notice on a periodic table too that some elements can have more than one charge. So some of them are written in this table for us, but copper, for example, if we look up Cu on the periodic table, usually they're written on the top right, the charges. We'll see that it has 2 different charges. It can be a 1+ or it can be a 2+. When we're naming something that contains copper, we're going to have to somehow tell people if it's a copper with a 1+ charge or if it's a copper with a 2+ charge. So how we do that is we use Roman numerals. So if we used a copper with a 1+ charge, we'd use the Roman numeral 1. And if we had a 2+ charge, we use the Roman numeral 2, like 2 sticks. A 3+ is 3 sticks, and sometimes we'll have a charge of 4, and that's an IV, is a Roman numeral for 4. So if that ever happens, just goes in brackets right after the type of element that we're describing. So we'll learn about it in a second. It's called the crisscross rule. But there's nothing behind this copper, right? So you're probably wondering why I chose a 2. But this 2 did originally belong to the charge of copper. So this 4, when we're looking at lead, belonged to the lead, and that's how we got lead 4 fluoride. So sometimes a little iffy on these numbers, but typically it's going to be exactly the number that's right here, typically. So anyways, the crisscross rule. So the crisscross rule is going to be how we determine which little numbers we put here. So we know how to name. We could look up the periodic table and see that Cu is copper. We can look up on the periodic table and see that chlorine is Cl and change that ending to "ide. But it's hard to figure out what little numbers we're going to put here. So that's where the crisscross rule comes in. So let's take a look. We want to see what we make between K, which is potassium, and S, which is sulfur. So what I need to do is go to my periodic table, find K, and find S, and look at what charges they have there. So if I find K, it's going to be in the very first column, and everything in the first column has a charge of 1 plus, or you can just write plus. Sulfur is a nonmetal, so we're going to look at the very small piece on the right-hand side of the periodic table and find that it has a 2 minus charge. The crisscross rule says that those two charges are going to swap places, so that this 1 now goes behind the S. You don't have to write a 1 though. And this 2 now goes behind the K. So that this is the chemical formula for potassium sulfide. To see how that works and how we have these charges is kind of going back to what we said an ionic compound is in the first place. We said that metals are going to give electrons to nonmetals and they will be statically bonded together. So if I have potassium, it has 1 electron that's possessing in its outermost shell, another potassium that looks the exact same, and they both donate that electron to sulfur. Sulfur is going to have what we call a complete octet. It's happy, has 2 extra electrons, so it's a 2 minus. That's where it came from. And this potassium, as well as the other potassium, are both going to be a positive charge. And this is also in the same ratio that we have for our overall ionic compound. We have 2 Ks, just like in our formula, and we have 1 sulfur, just like we do in our formula. So then there is a whole bunch of questions going both ways. So we have going from the formula and writing out the name, which sometimes is people's favorite way to do it because it's easier. You don't have to really worry about the numbers too much usually, except for a bonus rule. So I wish I had a way to write on this, and I apologize that I do not. I is a very hard one because, as we'll see, we have Sn, which is actually tin, and O, which is oxygen, so we probably have tin oxide down. But when you look up tin on the periodic table, and I'm sorry I can't exit this program because then it doesn't actually follow me to the new page that I open up. But if I were to look up tin on the periodic table, I could have a 2 plus or a 4 plus. So this 2 is telling me that I'd want to write the Roman numeral 2, right? That would make sense. However, we also, when we do a crisscross, try to get into kind of that lowest common denominator type of stuff. So if we look at the periodic table, we can see that oxygen has a 2- charge, right? But there is no 2 after SN for tin. The thing is, we did have a 2 here at one point in time, and we crisscrossed that oxygen with a tin 4, so there was a 4 here. We had a SN2O4, and then we divided the whole thing by 2, the lowest common denominator, and made it this SnO2 instead. So sometimes there are some tricky pieces when it comes to putting Roman numerals in. This second one here, FeS, is another example of that. So it's a little bit more obvious because when we go to the periodic table, we'll see that iron can either be 2 or 3, but there's no numbers here at all. So that's kind of like, you're like, ooh, there's no numbers. Maybe we had some sort of like lowest common denominator and divided stuff out. So to figure that one out, we go to sulfur. We say, hey, sulfur should have a 2-. So there should be a 2 behind this Fe. How could that possibly be canceled out? So if that 2 went missing, there must have also been a 2 behind sulfur in order to cancel both out and make them both those invisible ones. So that's how we know it's a iron 2 sulfide. Just quickly looking at the others look okay. I could totally be wrong I'm wrong that PbO is also a lowest common denominator, but it works the exact same way as this FeS, where lead was 2, oxygen was 2, and we ended up canceling things out. Anyways, so a whole bunch of going from formula to name, and we also have name to formula. So if we're going name to formula, we're going to have to do those crisscrosses. We're going to have to go to the periodic table, look up aluminum, we'll find that it's a 3+, go to the periodic table, look up sulfur, notice it's a 2-, and they swap spots. The 3 now goes to the S, the 2 now goes to the aluminum. Sometimes it's nice to have Roman numerals because you don't even have to look it up. You know that this copper is going to be a 2+ because it just told you, right? Oxygen is going to be a 2-. They're both 2's, so instead of writing Cu2, O2, we divide by the lowest common denominator, that 2, and we're left with CuO. So there's lots of questions because this obviously, it just takes a lot of work to get down. So do as much as you need to do in order to understand what's going on. O is another one of those guys that we end up using a lowest common denominator. Anyways, so a lot of practice questions for you to do before we get to our next type of naming, which is molecular or covalent compounds or molecules. So these are a little bit easier when you look at your periodic table because they're only going to use nonmetals now. So that tiny little wedge on the right-hand side of your periodic table is all you really have to look at. All the metals on your periodic table will not be involved in these because if they were, we'd have an ionic compound. So a special type of molecular would be diatomic elements. So these are things that you've probably heard and discussed before, but maybe not put a name on it. Di meaning 2. We've got 2 of the same elements within the same molecule. So like O2 gas, we have 2 oxygens. Or hydrogen gas, we have 2 hydrogens. And this can't happen for just any element. There's only certain ones that we can do it with. So this is kind of our memory device for it, and I call it Hofbrinkel. So hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine are the gases that can do this. All of these can be diatomics and just be like an N2 gas or Cl2 gas. So not everything can do it, just this exclusive group. The rest we'll name using these rules. So still using crisscross. So if we wanted to do methane, which we'll learn more about in our next unit, we'll do carbon, and hydrogen, look up what their charge is on the periodic table. Hydrogen is a weird one. Hydrogen can actually go on the end sometimes instead of only at the front, and it's as far left as you can get on the periodic table. So it's not actually a metal despite being over there. It just has a lot of the same properties as most of the group 1 elements, but we can have hydrogen as a 1-. So carbon's going to be a 4+. We swap where those numbers go. The 1 now belongs to the carbon, which we don't have to write in, and the 4 to the hydrogen. So that's our final formula. Silicon dioxide. Silicon's kind of right underneath carbon on the periodic table, so it's got the same charge. And probably by now you wouldn't even have to look up oxygen's charge on the periodic table. You've seen it so many times. It's 2-. They swap spots. That 2 now comes behind the silicon. That 4 goes to the oxygen. We notice, hey, they're both even numbers that are divisible by 2. So why don't we divide them both by 2, the lowest common denominator, and just get SiO2 instead? Which kind of makes sense, right? We've got dioxide, so why would we have 4 oxygens for something that's dioxide? We only need 2. So some of this will make a little bit more sense in a way, but we have some extra rules. So some things are known by their common names. Methane is obviously not something you would have named off a periodic table. You'd probably call it carbon and then something hydride. Same with these guys. H2O2, not to be confused with water, which is just H2O, is hydrogen peroxide. So that's stuff that's usually in your medicine cabinet in a brown bottle. And then NH3 is ammonia. We could obviously name these in different ways like we have been, and we can if we wanted to, but there's other ways that are quicker like this, that people have an easy understanding, especially if they're not really in the chemistry world. So we had dioxide. We know things like carbon dioxide and carbon monoxide and things like that. So that's where this next part's coming from. We're going to have to use some extra prefixes when we make names for covalent or molecular compounds. So most of these prefixes are probably ones that you've used before, if not, honestly, just learning your shapes in elementary school. So mono and di mean 1 and 2. Those are the things we know from like carbon monoxide and carbon dioxide. Tri, like triangle, means we have 3 of something. Tetra is for 4. And then we kind of get into those shapes. Usually people know these from shapes, like a pentagon has 5 and a hexagon has 6, heptagon, octagon, 7 and 8. So these are some prefixes we're going to need to know. The only big thing that happens is mono is only used for the second element in the molecule. We don't call it kind of monocarbon monoxide, it's just carbon monoxide, right? But if you have multiples of the first element, we'll use any of the other prefixes. So let's see what that's like with things I've already talked about. So these are nice examples because we already know the name to them, so we can check our answer. So carbon monoxide, exactly how I said we don't say monocarbon because it doesn't need to have anything on the front. Different from carbon dioxide because there's 2 oxygens. Still looking at having a carbon out front, okay. Now we have 4 fluorines. So 4 is tetra, we have a tetrafluoride. So we're still changing everything to ide, right? We're just using new prefixes if we've got a molecule or a covalent. I am going to bypass these drawings because we didn't really cover it, but let's give it a go on some other stuff. So just picking things at random, here's something that finally has a number for something out front. So that's when we need to start using a prefix for our first element. Instead of just saying nitrogen, because there's 2 of them, we now have to say dinitrogen. We have 3 oxygens, So instead of saying just oxide, we have a trioxide. That's how we can tell this is a covalent or a molecule. Again, anything that you have two of out front, make sure you use the di. But if it's just one of something like F, H, and J, you can just use the element's name, and we're good. And then going in reverse, going from name to formula, is much nicer actually, because you really don't have to consult the periodic table. If you have dinitrogen, you know you have two of them, so N2. Tetraoxide, you know you have 4 oxygens, so O4, and you're done. We don't have to take this into the lowest common denominator because it already told us what we're dealing with. We want to make sure these numbers match what these prefixes are telling us. And a whole bunch of questions. So when we said there were some common names for things like ammonia and methane, we could name it using that formula. So nitrogen trihydride or carbon tetrahydride if we didn't memorize these two names. Same with water. We could have dihydrogen oxide or trioxide for ozone. Anyways, so we've done ionic, we've done covalent. We're going to look at polyatomic ions as well, which is actually kind of a subsection of ionic compounds. So we're going back to the first type of names we've learned, except these ones are a little bit harder because polyatomic ions aren't found on the periodic table. So a polyatomic ion is already an ion, something that's charged, but it's already a whole group of atoms together that are already bonded. And this entire group is going to end up bonding to another atom. So if it's a negative charge, we know it's going to be the last thing in our name. This whole carbonate ion could bond to a metal. So it could bond to a calcium, or it could bond to a lead or a copper, bonded to this massive thing. This nitrate thing could do the same. So it's negative, it's going to be the last part of the name. It could bond to a metal. Most polyatomic ions, you'll notice, does have a negative charge. The only one that goes at the front of the name, the positively charged one, is going to be ammonia. So ammonia would bond to a nonmetal, and ammonia would be the first part of the name because it's the positively charged stuff. So you could have ammonium chloride or ammonium oxide or ammonium chlorate, and it could bond to another polyatomic ion. Don't mind me about bicarbonate. I'm pretty sure it's right here, and I just wrote it in anyways. So polyatomic ions, we're just treating the exact same way. The only weird part is we can't go to the periodic table for the naming. We can go to a chart like this. So anyways, we still do the exact same crisscross rule if we are bonding that carbonate that we saw above with a metal, Ca. They both have the same charge. So if we were to crisscross this, we'd end up having a 2 behind both of these. We cancel them out, so we just have CaCO3. We have calcium carbonate. Sometimes, though, numbers won't cancel out. This is all askew. And that should also be a 1, I'm sorry. So that's that one polyatomic that has a positive charge. There's ammonia. And SO4 2-, if we scroll up, is sulfate. And it's a 2-. That's where we have this charge. So this 1, just like we did before with other ionics, is going to end up going to the SO4. And this 2 is going to end up with the NH4. So we now have 2 numbers in a row. If this 2 goes behind this 4, we have to separate them somehow. So that's where these brackets pop up. So we still have NH4 as a group all together, showing that it can't separate. This is fused, this polyatomic ion, and we have 2 of them. It will kind of be like if I had 2 carbonates, I'm going to draw this whole molecule twice. I would end up drawing this whole molecule twice. And because we only have one of the SO4, we don't even have to write in that one, so we don't need any brackets to show that. So brackets will sometimes pop up, making these things look pretty scary. So that's really short on polyatomics because it's just a little extra from the ionics we just learned about. Naming acids is kind of short too, because honestly it's not something we really have to memorize too much. There's two types of acids. There's the binary acids, which are the simpler looking ones, and there are the oxyacids. Oxy because they have oxygen. So acids will also be pretty recognizable because they'll always have hydrogen at the start. So if we're looking at binary acids, we're combining hydrogen at the start with some sort of non-metal and calling it hydro for what we have at the start of our name, and then the non-metal with an ic acid. Ic acid. That N should obviously not be there. Sulfuric acid. So fluorine, chlorine, bromine, they're all a 1- on the periodic table. So when they ended up crisscrossing, we have no numbers here. Sulfur is a 2- on the periodic table, and that's where that 2 came in. So those are binary acids. We just have hydrogen with one other thing, 2 stuff. Oxyacids, we now have oxygens in there, and they're the acids of polyatomic ions. So we've added an H to some of those polyatomics that we had in that last chart we saw. So the numbers that are behind the H come from whatever charge the polyatomic originally had. So phosphate is PO4 3-. If we check the last table, that 3 ended up being crisscrossed and became phosphoric acid. So these are ones that you kind of just reference in the table instead of memorizing. Anyways, one other important thing, it doesn't really come in too much, it won't be on your assignment, but just making sure that we count atoms correctly because it will be handy when we get to a further unit. Once we have brackets, it's kind of hard to understand how many different atoms we really had. So this is the same molecule we had before, or sorry, it's not a molecule, that's an ionic compound, where I said this is ammonium, and we have 2 of these. That's what that 2 says. So I have an NH4 if I were to draw it out, and a second NH4 that looks the exact same. So if we were to count how many N's we have 2, because we have 1 in the first NH4 that I've drawn, and 1 in that second NH4 that I've drawn. If I want to know how many H's I had 4 in that first NH4 that I draw, and another 4, so I have 8 total. The easier way to figure that out would be 4 times 2. Then this SO4 is all on its own. So I have 1 S because there's no brackets, there's nothing I'm multiplying, and 4 oxygens. Again, there's no brackets, there's nothing I'm multiplying by. I just want to see if there is a harder one down here, but I don't believe so. So there's a few extra ones that you can do. Again, if you have brackets with something outside, we're multiplying. This 3 though only counts for the stuff in the brackets in front of it. It won't come into play with the AL out front. So that 3 does not multiply by that 2. We'll only have 2 aluminums when we look at that kind of stuff. And that's everything.